So here we want to do, now that we've introduced triple integration, we want to do another example of triple integration, but one where it's not just a volume calculation. Again, sometimes it's called a volume integral that we're doing here, but we're not calculating volume. We're integrating a function over a volume, so I like to call it a triple integration. Okay, we've belabored that point enough. This is actually problem 4 from section 915 of ZIL. So the problem statement says, calculate the integral of 4x squared z cubed. So that's the function, the integrand. We're integrating over some triple region. Over the volume in the first octant, so x, y, z all greater than 0. And then closed by a couple other curves. Y equals z squared and x equals 1 minus y. This is a plane because we're first order polynomial in x, y, z. Z happens to be 0, but it doesn't depend on z. Here we have a parabolic type of relationship. Again, doesn't depend on x. So, okay, we're integrating this thing over the region defined by those curves. So 2 different sets of functions. We have to plot it to visualize this and decide what order of integration we're going to do. I've gone ahead and done it because it's a kind of not super tricky, but not super easy to draw. That's the way it looks. So here's my 3D sketch of it in x, y, z. Right? I've got this bent curve, okay, that hits this x-axis. If you look at it from, in this case, I've gone, and you should do this too, is look at some projections. So just look down at the z-y axis. Okay, so turn this and just look in this section here. The y equals z squared curve is a parabola, starts at the origin and increases rapidly along y with increasing x. So y equals z squared, right? And the plane, I've kind of tried to draw in blue here, which is y equals 1 minus x, or x equals 1 minus y, same thing. And it's actually going to intersect the yz plane at y equal 1 and be a vertical cut through there. So it's an angled plane, vertical in the z direction, that cuts a little bit of this funny curvy curve out. So again, look from the front down, we see this curve, and that would be the intersection. If you look down on the yz plane, we just see we would have the big curve coming up like this. Okay, so it'd be coming out of the board up here, right? So as x got bigger, y got bigger. But then we're cutting it down here. So this is the vertical view of this plane, y equals 1 minus x. Okay, so it's this region inside here, and inside here that we want to integrate this function over. So what coordinate system should we be in? Well, this is pretty naturally Cartesian. There's no indication that polar or cylindrical or spherical, which we haven't talked about yet, would help. What order are we going to do the integration in? That's the decision. That's the primary decision in triple integration. So here, I've got a z function as a height over the xy plane, and then I've got this region in the xy plane defined by this little triangle. So this seems attractive to integrate z first. So integrate down first, and then I'm integrating over this r. And then I have a choice of am I going to integrate y first or x first, and we'll do y first. Okay. So the order is z first, and z will go from 0, because we're in the first octant, so the bottom of the region is z equals 0, then up to this curve. Now that curve is said y equals z squared. We have to convert that to z as a function of x and y. So z equals the square root of y. So z goes from 0 to square root of y. Okay. Then we'll do y next. What does y vary from? Well, once we flatten this down in the xy plane, y goes from, well, 0 up to 1 minus x. Right? So y varies between those. And then finally, when you're done, x varies from 0 to 1. So those are the limits of integration. Now we set it up, and then we just execute it out. In, for example, like the final exam from the 2024 NMM 2026 course, we would have a problem not like this, but sort of like this, where, again, all you have to do is set up the integral. So you get to this next point here, and that would be the answer to the question. You actually have to execute the whole thing. That may or may not happen in any given year. Okay. So our integral, I'm just going to call it I. So I is, okay, it's the triple integral. Okay, I'll just write it formally first. So this is that's what we're doing. Okay, now we've got our limits here. So x is 0 to 1, y is 0 to 1 minus x, z is 0 to the square root of y. And I've got 4x squared z cubed, and then I write these in dz, dy, dx. Innermost, nextmost, nextmost. Okay. A very, very, and so in that previous final, this is the answer. You write the form of the integral, you get the integrand correct, you get the dv converted, you have the limits of integration all correct. That was the whole question. It was a short question, but that was the question. You had to plot it and set this up. Most common mistake, probably the most common mistake in setting this up is people, it's right here. You go, well, I'm going to integrate in the z direction first, so I go from 0 to z squared. And they write 0 to z squared here. Because they're not really thinking clearly, and they know they want to go from the bottom up to this curve, and then they think, oh, this curve is z squared. Well, it's y equals z squared, but I need to go up along z. So I need to solve the curve as z as a function of x and y. But I've definitely seen people write 0 to z squared here, then go through, and it all is a disaster, because then the end of that integral is still a function of z, and your final answer looks like a function of z, and it doesn't work. Okay, so that's the number one mistake. Okay, so now we can just go ahead and execute this. Now I'll go through this motion because that's what this exercise is about. Okay, so we're doing z first. So we've got, okay, 0 to 1, and we're 0, 1 minus x, and then 4x squared is the constant. Then we have z to the 4th over 4, right? That would be, and then that's evaluated at square root y and 0, and then we have dy and dx left. Yeah. Okay, so we put that in, and so this will just be, I'll take the 4 out the front, 0 to 1, 0 to 1 minus x, and I've got x squared, the 4, and the 4 here would cancel that 4, so I didn't have to do that. Then I've got x squared and z to the 4th, and then put square root of y, so that becomes y squared. Okay, minus 0, so I don't need that part. And then we have dy, dx. Yep. Okay, so I'll just do one more step here. So now I'll integrate the y part, 0 to 1. Then x is a constant with respect to x squared. Then we have y cubed over 3. Put brackets there if you want. Then we go 1 minus x to 0 dx. Okay, now we put that in, and we'll have a function of x alone. So I'm going to go over here and just leave the diagram up. Okay, so over here, so I equals, right? Okay, so we got, that's 1/3, 0 to 1. We got x squared, then we got 1 minus x to the 3rd, minus 0, dx. Okay. So now we got to blow this thing up into a set of polynomials, and then we'll integrate them all out. So I've got 1 over 3, 0 to 1, x squared, and then my notes I have this. Okay, let's just do this. So you don't have to do it all triple. I would just go like 1 minus x, and then I have 1 minus 3x plus x squared dx 1 x squared 1 minus 3x plus x squared minus x plus 3x squared minus x cubed, and then we have 1 over 3, 0 to 1. Let's just see, can I do anything here? So I've got, let's go slow here, 1, and then the x's, so minus 4x plus 4x squared minus x cubed dx. Right, so this becomes 1 over 3, 0 to 1. x squared minus 4x cubed plus 4x to the 4 minus x to the 5th. Let me just check my notes here. Let's see, this is, nope, something's wrong. X, let's see here. 1 minus x, so 1 minus x squared is 1 squared. Oh yeah, right here. That should be, this should have been, because this was 1 minus x squared. So that should be 2x plus x squared. Then I should have gotten 1 minus 2x minus x squared minus x minus 2 plus 2x squared minus x cubed. So this becomes 3, this becomes 3. Okay, and then this becomes 3, this becomes 3. Okay, that's better. Okay, let's just do the next step here. We can do it right here. 1 over 3, and then we have x cubed over 3 minus 3x to the 4 over 4 plus 3x to the 5 over 5 minus x to the 6th over 6. 1, 0. So 1, 0, so we're just going to have this whole thing at 1. So, okay, let's go over here. So, back up here, I equals, so we have 1/3, okay, 1/3, then we have 1 over 3 minus 3 over 4 plus 3 over 5 minus 1 over 6, okay, so then we would have 1 over 3, this is 12, so 4 minus 9 over 12 plus 18 minus 5 over 30. Okay, so that would be 1/3, and we have minus 5 over 12 plus 13 over 30, so that would be 1 over 3, and we have minus 5 times 30 plus 12 times 13, 12 times 30, 360, so this becomes 1 over 3 minus 150, and we have 120 plus 36, so 156 plus 156 over 360. Okay, so this becomes 1 over 3, 6 over 360. So this becomes 2 over 180, or the, 2 over 360, right, or 1 over 180. Okay, that's our final answer. Okay, a little tedious, right, a little tedious as we get through, but we can certainly do it. You can see why, like on the exam questions sometimes, the higher mental activity part of the problem was setting up the integral. Executing the integral there was just an opportunity to make a bunch of mistakes, as did I, which I often do, right? So you got to work out the polynomial part, and I know we know how to do this. It's easy to make a mistake in it, but so often I don't ask this part on an exam. Sometimes I do. I mean, it's totally fair. You can do it. It is math, but sometimes we don't bother. At the very end, right, as usual, we try to make sense of it. Does this number make sense? So This is not a volume calculation. This was an integral of a function. I erased the function. The function we were integrating, remember, was it 4x squared. We were integrating 4x squared z cubed, okay? And we were integrating it over a region where we were in the first octet, right? So this thing we were integrating over is positive everywhere that we were integrating over, okay? So we're integrating a positive number over this region. So the answer we get in the end actually should be greater than 0. When we do a volume calculation, you know the answer is greater than 0. When you integrate a general function, you don't know for sure. It's fine for the answer to be less than 0. It depends on the function or the integrand that we're using. Here, we can look at it and say, oh yeah, this whole thing is positive over the whole region, so the answer should be greater than 0. Now, should it be less than 1? Well, we are integrating a pretty small region, right? We're integrating in this little region where everywhere, everything is less than 1, okay? So we've got a whole bunch of fractions, x and y and z are all less than 1, and we're integrating like x squared, z cubed. So, you know, if they're on the order of even 1/10, this thing becomes 1/10,000th, right, or something like that. It's a small number. So it does actually make sense that our answer is small. We shouldn't get an answer that is 10. We shouldn't get an answer at 24 pi. It makes sense we get an answer 10 to the minus 2. Yeah, actually it does kind of make sense. So again, in the spirit, you should try this all the time, is to just make sense of it. And you can't always make much sense of it, but often you can. Anything you can do is helpful. Actually, in the note module, so this problem I did in the triple integration note module, and in that module, when I first did it, I made a mistake. Not this mistake, I made a different mistake. Actually, I made a mistake in that one right here. I think I had a 6 there instead of a 5. And I found it in the notes, but I left the error in there. And I was trying to show in the notes that when I did it in that case, actually I got minus 1 over 180. And at the end I said, okay, let's see if this makes sense. I went through this exercise and we say, well, geez, the answer should be positive. That indicated I made a mistake. And then I went back through and I kind of found I was correct to here, and then I just wrote a 6 here instead of a 5. I could find it and then went through and fixed it. This is also a lesson. If you are doing this kind of calculation, you really should do this many steps, right? And even here when I did it, actually, where's the one mistake? Where's the one place I made the mistake? I went from 1 minus x cubed, and then in my head, I did the 1 minus x and 1 minus x squared. I didn't write this out separately, and I made a mistake, and I put a 3 in there by accident. Every time you try to do too many things in a step because you're so smart, like me, I say the same thing, well, I can do this in my head, you are risking it. The best thing is you just take one thing at a time. It is not faster. You do not gain speed by skipping steps, because you might make a mistake and then you have to go back and find it. Right? So you want to do each of these steps like this. And again, the reason is when you get to the end and have a wrong answer, then you go backwards and go, well, all right, let's see where the mistake is, and you can kind of work it out. Okay, so that's just another me ranting about trying to do this in step by step, right? So that will save you time in the end. Okay. That's our example of a general case of triple integration of Cartesian coordinates. Now we're going to move on to, if I remember right, we move on to divergence theorem and then go back and talk about other coordinate systems.